All right, let's talk about amines. If you're getting ready for your Class 12 exams, you know this chapter is a huge one. But don't worry, we're going to break it all down and make it super simple. Let's just dive right in. So here's the game plan for today. First, we'll cover the absolute basics. Then, we'll get into how to actually name these things. You know, the rules. After that, we'll look at the 4 main ways to actually make amines. Then, we'll check out their basicity and some key tests. And finally, we'll put the spotlight on diazonium salts. Sound good? Let's go.
Okay, Section 1, the basics. So, first things first, what in the world is an amine? Let's get that foundation locked in.
You know, it's actually a pretty simple idea. Just picture an ammonia molecule, right? NH3. Now, all you do is start swapping out those hydrogen atoms. You can replace 1 or 2, or even all 3 of them with some kind of alkyl or aryl group. And that's it. The number of hydrogens you kick out is what tells you what kind of amine you're dealing with.
And this table here just lays it all out for you, nice and clear. See, if you swap out just 1 hydrogen, you get a primary amine, or 1 degree. Swap out 2, that's a secondary, or 2 degree. And, you guessed it, replace all 3 hydrogens, and you've got yourself a tertiary amine. It all comes down to one simple question. How many carbon groups are stuck directly onto that nitrogen atom?
All right, Section 2, naming amines. So now we know what they look like, but how do we talk about them? You've got to know how to name them, especially for your exams. Let's get into the rules.
So, you've basically got 2 systems for naming these guys. First, there's the common name, which is super easy. You just take the name of the alkyl group and tack on the word amine. So, ethylamine. Simple, right? But then you have the official IUPAC name, which is what you'll see on tests. For that one, you find the parent alkane, like ethane, you drop the final E, and you add amine. So ethane becomes ethanamine. And if the carbon chain gets longer, you just slap a number on the front to show where that amine group is attached. Easy peasy.
Okay, Section 3. Now pay close attention here, because this section is an absolute goldmine for exam questions. We're going to walk through the 4 most important ways you can actually make amines.
First up, we have ammonolysis. The idea is simple. You have ammonia attack an alkyl halide. But there's a big catch. The primary amine that you just made, well, it's also a pretty good attacker itself. So it goes and attacks another alkyl halide, which makes a secondary amine. And guess what that does? Yep, it attacks again to make a tertiary one. It's this whole chain reaction that leaves you with this messy, chaotic mixture of all 3 types of amines. So yeah, not the best method if you're trying to make just one pure product.
Method 2 is the Mendius reduction. This time, we're reducing nitriles. Now, the really cool thing to notice here is what happens to the carbon chain. We start with a nitrile, the CN triple bond, and we end up adding a CH2 group next to the nitrogen. What does that mean? It means we've just added a carbon atom. This is what we call a step-up reaction, and it's super useful when you need to make your molecule 1 carbon longer.
Okay, method 3, Gabriel phthalimide synthesis. Now, I know this one looks a little intimidating with all its steps, but trust me, it's actually brilliant. It's a super clever process that was designed specifically to fix that messy mixture problem we saw with aminolysis. By using this phthalimide molecule as a sort of protective shield, you can control the reaction perfectly to get only a pure, clean primary amine. It's a fantastic method for that.
So if the Gabriel synthesis is so great for making primary amines, why can't you use it to make any primary amine? Like, for example, why can't we use it to make aniline, which is an aromatic amine? Take a second and think about what's actually happening in the reaction.
And here's why. It all comes down to that second step. That step is a nucleophilic substitution reaction. The problem is, aryl halides, things like chlorobenzene, are notoriously stubborn. They just do not want to do nucleophilic substitution. That phthalimide anion we make, it's just not powerful enough to attack that stable benzene ring and boot out the halogen. This is a really, really key concept, so make sure you remember it.
And our 4th and final method is the Hoffman-bromamide degradation. The name itself kind of gives it away, right? Degradation. You start with an amide, and this reaction literally chews up and spits out the carbonyl group. It just gets kicked out. So what are you left with? An amine that has 1 less carbon atom than the amide you started with. This makes it the absolute classic step-down reaction, the perfect opposite to the Mendius reduction we saw earlier.
All right, Section 4. We know how to build them, so now let's figure out how they act. Understanding their basicity and a couple of key lab tests is crucial.
So why are amines basic? It all comes down to one thing. That lone pair of electrons sitting on the nitrogen atom. It's just hanging out there, ready and willing to be donated to a proton or an H+ ion. And that act of donating an electron pair, well, that's the very definition of a Lewis space. Honestly, if you understand this one simple fact, you're halfway to understanding almost all of their chemistry.
Okay, let's talk about how to spot these guys in a lab. You need to know two essential tests. First is the carbylamine test. This one is your sniper rifle. It only works for primary amines. If you run the test and get this absolutely horrible, foul-smelling isocyanide, congratulations, you found a primary amine. Then there's Hinsberg's test. This one's more of a detective's tool. It helps you tell the difference between primary, secondary, and tertiary amines by seeing how they react with this thing called benzene sulfonyl chloride.
And that brings us to our final section, a spotlight on diazonium salts. Seriously, you guys, these things are one of the most useful and versatile tools in all of organic chemistry. I like to think of them as the Swiss Army knife for making aromatic compounds.
So what makes them so great? Well, they're amazing because you can easily replace that entire diazonium group with a whole bunch of other things. The Sandmeyer and Gatterman reactions are perfect examples. They both do the same job. They stick a chlorine onto the benzene ring. The only tiny difference between them is the catalyst you use. For Sandmeyer, it's a copper salt, like CuCl. For Gatterman, it's just plain old copper powder.
But maybe the coolest, and definitely the most colorful reaction they do, is called a coupling reaction. This is where you take a diazonium salt and react it with something like a phenol or an aniline. What you get are these things called azo compounds. And because of their structure, these molecules are almost always brightly colored. In fact, this is the exact chemistry behind a ton of the synthetic dyes used in clothes and all sorts of other stuff.
All right, to wrap things up, I've got a little challenge for you. How would you convert methanamine, which has 1 carbon, into ethanamine, which has 2? Think back to those 4 preparation methods we talked about. One of them is the perfect step-up tool for this exact job. Give it some thought. And hey, thanks for joining me for this deep dive into amines.